Okay, so coffee cups, calorimetry. This is really the focus of labs that we do in this class. This is a um, pretty easy topic for us to get good results in and match them to resources that we have. So like known values and charts and things. So what do we got here? Coffee cup, and it's a nested coffee cup, which means that we end up using a couple of coffee cups. So we nest them. So we usually use two. Styrofoam is actually a significantly a very good insulator. And so if you look at this, you're like, oh, that doesn't seem very high tech. Well, it's not. But styrofoam is an incredibly good insulator. And so we usually don't have a second hole for a stirring device. We usually just use the thermometer to stir. That is not recommended, but it does limit the holes in the lid to one instead of two, which does help our values. The things that we put in here cannot get too hot because they would melt the cup. So we're going to be doing things that have small amounts of heat, but we do get very good data when we do this. And so this is kind of what we talk about with the calorimeter. We're going to use coffee cups, styrofoam cups, but you could use something super fancy. You could use some sort of metal calorimeter or something like that, where you have a nice closed system. But we don't have that. It doesn't. It's too expensive for us to have things like that. And the values we get very good results. So we take a look. Calorimeter. It says we use a basic coffee cup calorimeter, so styrofoam cup. It says polystyrene is a good insulator. Very little heat flow through the wall, so we're not losing a ton of the heat this way. We're able to measure most of that in here in the water. So that's the good thing, is that we're not losing a lot of our heat. So first key thing to note is right here is to use a coffee cup calorimeter, you have to have a small amount of heat. So you're restricted to experiments where you're not going to melt the cup. So we're not going to be able to do certain things. Okay, definition here. Specific heat. Specific heat is a value that we will use. So specific heat is the amount of temperature. It's the amount of heat required. Amount of heat required to change the temperature of a substance by 1 degree Celsius. So we can change 1 gram, 1 degree Celsius. How much heat does that take? So things that take more heat are less resistant to temperature changes. So water is actually fairly resistant to changes in temperature. It has a very high specific heat. This is water specific heat. This is given to in your data booklet, but you're going to use this number a lot. This is a very, very useful value. So this is going to be very useful. So you might want to put a star by that. And if you look at other specific heats, other C values, like metals will have much lower values. Well, if you think about metals, you put metals at home on your stove and you heat them up. Well, they heat up quickly, they cool down quickly. Same thing with the opposite thing happens with the water. So think about got a pan here. And if we put water in that pan and we want to get it going, well, that pan gets really hot way before that water starts to boil. The water has the high specific heat, very slow to change, and the pan has has the low specific heat, so it is going to change rather quickly. So think about places that are next to water, right? So you live next to water, so you live in California. Well, normally places that are next to water, California, Hawaii, etc., what happens is that the huge amount of water that's sitting next to them, it keeps the temperature in a very small range. It's not like Kansas City where you see massive changes in temperature in winter and summer, and we have real high highs and real low lows. It keeps all the temperatures sort of in the middle. Well, that's because it takes a ton of energy to heat up the ocean because it's made of water. So it doesn't change its heat that much. It doesn't get really hot, doesn't really get cold. It doesn't switch its temperature a lot. So anyway, so what do you need to take away from this very long discussion on C? Well, you really just need to know the formula. Here's the formula. Q is heat equals mass, so we can measure mass of the water, times specific heat. We know specific heat of water times the change in temperature, which we can measure. So note, change in temperature is going to be, and if you have physics, you probably know this, but it's final minus initial. So we're doing temperature, it's final minus initial. So final minus initial. And that's for temperature. And then there you go. There's some values. You can rearrange it, play around with it. But so we're going to have delta T over here. And then our heat change is our Q value. And then there's our unit. And the unit does become important because the unit is joules, not kilojoules. So the problem is that if you use this formula here, you're going to get joules. And if you're playing around with delta H's, then those are kilojoules. So we'll have to make those work out together and play nice together. And so that can be a bit of a challenge for students. So, all right. So then I'm going to talk about this here in a minute, but this is what students really, really struggle with conceptually. So if you have water and it's heating up, what happens is that the heat is absorbed by the water, so the water's temperature goes up. So the heat is going into the water. So the water then gives us a positive value. So it goes from 20 degrees to 30, right? Okay. Here's the problem. That's a positive value, and that looks like that's endothermic, right? Plus is endo. So you get a positive value, and that looks like it's endothermic. But here's the deal. The heat went into the water. The water is just helping us measure what the heat is doing. So the heat goes into the water, and the water's temperature goes up. So what we have to remember is that whatever happens to the water, it's the opposite for the heat. So the heat is pushing out. So that's a negative sign, exothermic. So let's read this right here. In a calorimeter, when heat is released, so heat going out by an exothermic reaction, it gets absorbed by the water. That's what I talked about here. The water has gained heat, so it's gaining heat produced by the reaction. So the reaction is negative, even though we're getting this positive sign for the water. So what do you have to remember? Right here. We switch the sign. So whatever the water is doing, the reaction is doing the opposite. So if you get a negative sign for water, it's cooling down, it's positive, it's endothermic. If you get a positive sign for water, it's a negative or exothermic. And so we just have to be careful. And here's what I'd tell you to do. Look at what happened in your reaction. Did your reaction heat up? If it's heating up and it feels warm, you know that's exothermic. Did it cool down? If it feel cold, then you know that is going to be endothermic. So I think you have to use some logic here and just kind of think about what's happening. And I think that will get you where you need to go. So I know that probably all sounded really complicated, but it's really not that hard when we kind of go through this. So let's do this example 5. So right away, the example says that we have a 10.5 gram sample of a metal alloy. It's heated to 19.10 degrees Celsius. It's dropped into 20 grams of water, which is a calorimeter, and the temperature goes up. Calculate the specific heat of the alloy or the metal. So the alloy, guys, is the metal. All right. So here's the problem. And you're going to have a question like this on the test, so you should probably say, hey, this is a test question. Always shows up. I have metal, and I also have water. I have two things going on. So we need to be able to figure those out as we go. Now we are going to use this formula, Q equals MC delta T. We are going to use that. The issue, though, is we're going to have to do this twice. Whoops. Because we have both water and metal. Okay, so we're basically trying to find C, specific heat. We're trying to find C of the metal, right? So let's look at what kind of information we have about the metal. So if this is the metal, so we're looking at the metal currently. What do I know? Well, I know how much it weighs. So I know it's M. I'm looking for specific heat. So this is my X. And I can find change in temperature, but I don't have Q. Here's the problem. You're missing two variables. You're missing Q and you're missing X. So that means we're going to have to figure out Q in a different way. All right, so let's talk about change in temperature. The metal starts at 99.10 degrees Celsius. You then put it into water, into a cup, and that cup has water in it. Now the water, before you dropped your hot metal in there, the water was at 18.51. And then what happens is that you drop in the metal and the temperature goes up to 22.03. So here's the thing students always struggle with. 22.03, that is the final temperature for both the water and the metal because, see, they equalize. So this is the final temp for water. I'm going to run out of space here, so I'll move this. I'll put it back in a minute. This is the final temp for water and metal because the metal cooled down. When it got dropped in there, it cools down. When the metal got dropped in, the water's initial temperature heated up. So the water's heating up, the metal's cooling down, and they're basically finishing in the middle, which is 22.03. Here's the problem students always have. They can't solve all the temperatures at once because there's two things. You got the metal temperature and the water temperature. So for this situation here, for the metal, it would be final 22.03 minus initial, which is 99.10. Okay, so if we do that real quick, 22.03 minus 99.10, you get negative 77.07. So that's going to go here. Negative 77.07.